Fusion Mobile, quality e-learning experience on the go.
Today we are discussing reflection of light waves. We're looking at the little cat looking into the mirror and seeing a lion. Okay, in reflection of light waves, you look at a certain reflexive object and you see your image back. But before we discuss that, I would like us to discuss objects and the type of objects we have. We have luminous objects and we have non-luminous objects. Luminous objects are those objects that can produce light on their own without any external optical effect, while non-luminous objects cannot produce light on their own. Rather, they can only emit or reflect an already produced light from luminous objects. Now we'll talk about rectilinear propagation of white light or light. It's referred to the phenomenon of light traveling in a straight line. It's real. We consider it a phenomenon. And this rectilinear propagation of white light has given room to some parameters in physics, such as eclipse, image formation on mirror, and shadows. All these are as a result of rectilinear propagation of white light. And in eclipse, we have about two types of eclipse, two basic types. We have the solar eclipse and we have the lunar eclipse. Annular eclipse is quite somehow different. With a well diagram after this topic, I will relate to you what annular eclipse is like. Then we can now go ahead now to define reflection of light. This is the bouncing back or away of light when it encounters an obstacle on its path of propagation. There are two basic types of reflection. We have the regular reflection, which we obtain in this form. This is the incident ray. Why? These are the reflected rays. For regular reflection, the surface of incident is a smooth one, such that all the incident rays are reflected in same direction, as shown in the diagram. This one is considered regular. Then we have the irregular. You can see on the second one, all incident rays on the surface are scattered in different directions. It is also called scattered reflection or diffused reflection. This is called irregular reflection, scattered reflection, or diffused reflection. There are two basic laws of reflection. The first one says the incident ray, the reflected ray, and the normal. My dear, listen to that. And the normal. It didn't say and the normal ray. No. And the normal at the point of incidence all lie on the same plane. Now let's use a diagram to show what that thing is trying to say. It's saying that the first law says the incident ray, you can see the incident ray, the reflected ray, and a normal. A normal here is a straight line that is perpendicular to the plane of incidence. This is the normal N, this one is the incident ray, and this is the reflected ray. It now said the incident ray, the reflected ray, and the normal. At the point of incident, three of them lie on the same plane. That's the first law. While the second law says the angle of incidence is equal to the angle of reflection. The angle of incidence must be equal to the angle of reflection. That means the angle of incidence somewhere here, small letter I, must be equal to the angle of reflection, small letter r. So that means I is equal to r. From here we can now derive the equation of deviation. What is deviation? First of all, that this particular ray is supposed to continue this way, but now it didn't go there as a result of something. What is the angular difference between where it's supposed to be, which is here, and where it is now, which is this place? So this is the deviation. And linear deviation d is equal to, looking at this from here to here, is a straight line, and we know that angle on a straight line is 180 degrees. So d will be equal to 180 minus bracket I plus r. That's the equation. But since I is equal to r, that means that d is equal to 180 minus 2i, or d equals to 180 minus 2r. Take note of these equations. They will be of wonderful help to you soon. So now we can discuss Miro's formula. Miro's formula, which is conventionally given in physics as 1 over f equal to 1 over u plus 1 over v, where f is the focal length, u is the object distance, and v is the image distance. We can also talk about the equation of magnification. Magnification is equal to image size over object size, or magnification equal to image distance over object distance. This can also be combined together, since magnification equal to magnification. We now have it that image size, which is conventionally given as I, over object size O, is equal to image distance V over object distance U. That means I over O will be equal to V over U. Please take good care of this equation, because you will use it to solve all problems in pinhole cameras and even on plane mirrors. Now I will take us on the trend of how to take a diagram on concave mirrors. But before then, let's take a little look on what I have told you before. Miro's formula: f there is considered as the focal length, u is the object distance, v is the image distance. Now we take the equations of magnification and then give you the equations when they are compared together. In taking a diagram on curved mirrors, we have two types of curved mirrors: the concave mirror and the convex mirror. Considering them, in concave, we have the internal part being the reflexive part of the mirror, while the external part is the reflexive part of the mirror of the convex mirror. We will discuss this later, but I want to take you on an exercise now. Bring up a graph sheet, place it in front of you, get a very wonderful ruler, then bring out your textbook and make sure you can get me the diagram or the ray diagram of image formation 1 on plane mirror, 2 on curved mirror when the object is placed at behind the center of curvature, B at the center of curvature, C between the center of curvature and the focus, D at the focus, and E between the focus and the pole. If it seems difficult, visit Divine Touch Volume 1, page 38, and you will see the full diagram with full explanation down there. But never mind, we will also talk about this when we move into Optics 2. Have a wonderful time for now.